So now let's apply those log properties, but go in the other direction. That is, we already have a sum or a difference, or maybe we have a lurking exponent, right? A coefficient, I should say, that I can make an exponent. And the goal here is to write this as one logarithm. Remember what we just did, we went from one logarithm to multiple. Now just think about this as going backwards. All right, so let's see. First thing I got to do, I got a plus, I got a minus. I know I'm going to have a product, and here I'm going to have a quotient. But first, I always got to deal with these first, the coefficients, and make them exponents, because they're going to mess up my ability to make this a quotient. All right, so step one would just be to make that 7 cubed. That guy's gone. And now apply, you can do it all at once, but if I did it one at a time, I'd say, okay, plus means product. So a single logarithm, base 2. Now these bases have to line up, which they do, of x times y. Plus means product. Minus the log base 2 of 7 to the third. And now I just have two logarithms and a difference, which is going to translate to a quotient. And the first part of that is the numerator, and the second part is the denominator. And we could raise 7 to the third if we wanted to. What is that? 7 to the third, 49 times 7, 3, 6, 28 plus 6, 343. So 343. All right. Take a second and try this next one. See if you can get it. Pause the video, give it a try. First thing I'll do is bring this 2 up here. So I got the log of x squared minus 1 minus the log of the square root of x plus 7, which we typically would write as a to the 1/2 power, right? We work with logs and exponents, not roots, so we can write this root as an exponent. However, once I bring the 2 up, I can see what's going on here. I'm squaring a square root, so those will cancel out. So that gives me the log of, and now I can work with the quotient, x squared minus 1 over the simplified form of this. And you might recognize something here. I got the log, the common log of x plus 1 times x minus 1. What I recognize is the numerator's factorable, and I can simplify this guy. That is for x not equal to -1. The log of x minus 1. But actually, do we even need this little distinct? I had to bring this in when I killed my denominator, right? Because I say, well, wait a minute, I got a denominator. X can't be -1 here. But now I don't really need this because the domain of this function, which we haven't really talked about yet a whole bunch, is that the log has to, the input has to be positive. That is, whatever this is has to be positive. Which means x has to be greater than 1. So it's kind of assumed this condition. If I'm not writing this condition, I definitely don't need this condition. But if we are writing our conditions, which we should be, then I also don't need this condition because -1 is less than 1. Okay, we'll talk about more of about the domain of these things here real soon once I get to my log as a function down here. Okay, but first let's do a couple quick application problems. We already did some in terms of the money. If your money grows n times a year, that's an exponential function. If your money grows continuously, that's an exponential function. And these ones are very similar. You'll notice this looks a lot like how much money you have right now is the initial amount, e to the rt. It's the same model as so this is how money grows if it's growing continuously at like 10% a year or something like that. Same model for population growth. In this case, if it's negative, it's decaying. So we already know if I have a negative exponent that it should, be a decaying function. So let's see if we can answer the question. P of t is the population after t hours. How long will it take to reach 10,000? Well, that seems to be a problem because this is not growing. So I need to edit this document. That's a typo. So I take that. This is a increasing function. Right? If I read carefully, it says population to reach 10,000. So that means this has to be positive. So I'll have to make that change in my notes. Okay, so how do I answer that question? So my function is, it starts with 500 bacteria, and it's growing according to this model. So we can look at the graph if we wanted to. That's an increasing function, should start at 500 and then increase. How long till it gets to 10,000? Okay, so the output's 10,000. So we've actually solved this problem before with the money question. So it's 10,000 equals, instead of equal to your function, 500 e to the 0.02t, and then solve. Okay, so I do some algebra first, divide both sides by 500. So that should be equal to 20, I believe. I'll have to use my calculator to make sure I'm doing this right, but I definitely need my calculator now. How do I solve this equation? Okay, so this is interesting. We haven't solved these guys yet, the log equations. So if I want to solve this thing, and we have a whole unit dedicated to solving exponential equations. Exponential equation. This is an exponential equation. The exponent is the variable. Okay, so think about this for a second. I'm going to take the natural log of both sides. Natural log, natural log. Okay, so we have a property for this. This is a property where the bases line up. Remember, natural log is base e. So I got base e and base e, so they cancel each other out. It just leaves me with the exponent. Oh, that's nice. But on the right, it's a little messy. I took the natural, or I'm sorry, on the left, it's a little messy. I took the natural log of 20. And there's nothing I can do with that except plug it into my calculator. This will be like a calculator kind of problem. I'm one step away from solving to t. I'm going to choose to do my calculator work all at once. And I've solved for t, right? I did algebra to solve for t. It's the natural log of 20 divided by 0.02. So what did we do that was new to us this step right here? We took the natural log of both sides. That's how we're going to solve exponential equations. Okay, we're going to do a lot more of those in the next unit, the next set of notes. We're going to solve a bunch of exponential equations. And logarithms allow me to solve exponential equations. Okay, so now I just go into my to my calculator in order to solve this, and I get 14.978 is what I got. So I'm just going to round that up. Let's see. I didn't tell you how to round, so I give you a lot of leeway in rounding. If you're doing your homework in my labs, it'll tell you how to round. If it says 2 decimal places, we would call this t equals 14.98, and that should be in hours. Okay, we'll do a bunch of those later in the next unit, a bunch of solving exponential equations. Let's take a look at this problem that uses logarithms to measure the intensity of an earthquake, which you might have heard before called the Richter scale. Okay, so that number of the Richter scale is based on this formula where m is the magnitude, I is the intensity of the earthquake, I naught is a reference intensity, 10 to the negative 4 micrometers. Okay, so an earthquake has an intensity 10 to the 6 micrometers, calculated magnitude on the Richter scale using logarithms. Okay, so this is just a plug and chug kind of problem. I think, say I is 10 to the 6, so just plug it in log base 10. By the way, we don't usually see that. That actually shouldn't be there. I think I just put that there to be sure that we're doing log base 10, which of course wouldn't be written. So this is how it should be written. I is 10 to the 6, and then I naught is given as 10 to the negative 4. And then we just simplify this. So we use our exponent properties. You're dividing, which means you add. You might remember 10 to the 6 divided by 10 to the negative 4 is you subtract the exponents, which in this case you end up adding since the denominator is a negative exponent. So that's really 10 to the 10th. So m equals the common log of 10 to the 10th, which has to just be 10, right? Because we have a base 10 here, and these guys cancel out, and it leaves you with the exponent. All right, let's talk about the log as a function now. So we've never really done this. We can graph this thing. So here's, if you went way back and graphed, you could just do x and f of x. and you pick a bunch of values. So we could do it like that, or we could use the inverse stuff, right? We did inverse. This is y equals 2 to the x. Remember how to find an inverse function? You switch x and y. X equals 2 to the y, and then you solve. Take the natural, or take the log base 2 of both sides. Log base 2. Use our property. The log base 2 of 2 to the y is just y. And log base 2 of x. Okay, so this is what we're working with, and what I'm telling you is that that's the inverse of 2 to the x exponential. So 2 to the x exponential, here's like the kind of the cheating way to do this. I could graph that because it's a lot easier. And then if you remember from that inverse section, it's a reflection around this line y equals x. So what I end up doing, if 0, 1 is on my exponential, 1, 0 is on my other one. And for example, if this is the point 2, 4, then I have to have 4, 2. And then if this is the point, let's see, what would this be? Negative 2, 1/4. Then I'd have to have 1/4 negative 2. And if I did that for all the values, I would get a function that looks like this. That's a reflection around the line y equals x. The other way to do that, to find this graph right here, would be to plug in a bunch of values, right? Like if I plug in 1/4, 1/2, if I plug in 1, if I plug in 2, if I plug in 4, if I plug in 8, right? What's the log? And this is the function I'm working with, log base 2. Input all those numbers into here, do the easy ones. Log base 2 of 1, 0. Log base 2 of 2, 1. Log base 2 of 4, 2 to the what gives you 4. That's 2. This is 3. Those are all points on this graph right here. And these ones are a little trickier. What's the log base 2 of 1/4? 2 to what power gives you 1/4? That should be negative 2. So 1/4 negative 2, and so on. Okay? And that's how log functions work. Log base 3 is going to look a lot like log base 2. The natural log of x is going to look a lot like this. They'll just grow at a slightly different rate, but they'll have the same domain, as you can see. The domain of this thing goes from 0 to infinity, which of course matches the range of my exponential function. And then the range of my log function, you can see on the graph, it goes from negative infinity, it's going to go up forever, negative infinity to infinity, which of course matches the domain of my exponential, that inverse property. Okay, so I know I'm not going to spend a lot of time. We spent some time on exponential function graphs. We're not going to do a whole lot with logarithmic graphs. I just want you to know kind of the basic graph of that guy. And then, of course, the domain question. So just kind of a bonus question here. What's the domain of this function? F of x equals the natural log of x. Well, that's just your standard log function. So the domain is 0 to infinity. Well, we could do something a little more challenging. What if I said, what's the domain of the log base 2 of 3x minus 1? How would you find the domain of that function? Well, remember, what you're taking the log of has to be non-negative. So you would just take whatever in there, if it's some kind of transformation, and make it non-negative. Sorry, I should say positive, not non-negative, because it cannot be 0. So make it positive. It has to be greater than 0. And then you solve that. All right, these are pretty easy, as long as you understand the concept. X has to be greater than 1/3, which means it goes from 1/3 to infinity. So in other words, whatever is in here, if there's something other than just x, then you'd have to set that greater than 0 and solve. Okay? So we got some log models. We won't see a whole bunch of these. We just saw one, Richter scale, sort of a log model. I could give you problems with these. We won't dive in as much as we do with the exponential models. But you could see some basic examples in your homework where we do some applications with logs.